This is our first lecture on MRI. Let's look at the objectives for today. After today's lecture, students will learn about magnetism and the magnetic field. Students will know about bulk magnetization of a sample and how it is affected by the presence of static and radio frequency magnetic fields. Students will be able to explain precession of atoms in a static magnetic field. Students will be able to describe nutation and explain how it is responsible for causing the MR signal. Students will understand MRI signal properties and how to define T1 and T2 relaxation. Students will also learn about MRI pulse sequence parameters, a few basic pulse sequences, and contrast mechanisms involved in T1, T2, and proton density weighting. At the end, we will look at some of the special pulse sequences based on spin echo and gradient echo. Magnetism was first observed in lodestone, a natural form of iron ore called magnetite. Lodestone was known to the ancients as early as the 6th century BC in Greece and 4th century BC in China. Magnetism is a physical attribute of lodestone and is mediated by magnetic fields. Magnetic fields are caused by moving charges or currents and the magnetic moments of elementary particles due to quantum spin. Magnetic materials have two poles, a north pole and a south pole, so a magnet is a dipole. Magnetic fields are described by two related quantities. B is the magnetic flux density and H is the magnetic field strength. These two are used interchangeably in common usage. A magnetic field is a vector field and its directions are indicated by the right-hand rule. The SI unit of the magnetic field is amperes per meter and the flux density is given by kilograms per second squared ampere or Tesla. A traditional unit is a Gauss. 1 Tesla is 10,000 Gauss. To put things in perspective, the Earth's magnetic field is about 0.5 Gauss or about 50 microtesla, while hospital magnets range from 0.3 Tesla for resistive magnets to 3 Tesla for superconducting magnets. This figure shows a simple bar magnet with two poles and with a magnetic field lines going from the north pole to the south pole. The second figure is of a solenoid, which is a cylindrical coil of current-carrying wire. The solenoid also has two poles, a north and south pole. Hospital magnets are made from solenoids. A characteristic of magnetic materials is the ability to get magnetized when placed in a magnetic field. This is called magnetic susceptibility. Different types of magnetic materials are characterized by their magnetic susceptibility. Diamagnetic materials have slightly negative susceptibility, paramagnetic materials have slightly positive susceptibility, and ferromagnetic materials are superparamagnetic materials with a large positive susceptibility. Diamagnetism is the weakening of a magnetic field by a material and is exhibited by water and calcium. Because organic materials contain water and calcium, organic materials are mostly diamagnetic. This image shows a low flux density in a diamagnetic material. Diamagnetic materials are weakly repelled by a magnetic field. Paramagnetism is the enhancing of a magnetic field by a material and is exhibited by elements like gadolinium and oxygen. Paramagnetic materials are weakly attracted by a magnetic field. This image shows denser flux lines in a paramagnetic material. Ferromagnetic materials are materials having a permanent magnetic field. Only a few materials exhibit ferromagnetism. These are iron, cobalt, nickel, and their alloys, and a few rare earth materials like neodymium and samarium. Now let's learn a few terms relevant to MRI by looking at the motion of spinning objects. In the presence of a force, a spinning object precesses. The bottom left image shows a gyroscope in motion. In the presence of the gravitational force, the gyroscope precesses. Precession is distinct from rotation. Rotation is the spinning of an object about its axis. Precession is a second-order motion. It is the rotation of a rotating object. Precession is caused by two vectors, an angular momentum and a force vector. When you try to speed up the precession of an object, the object does not speed up, rather its precession angle changes. This is a third-order motion called nutation. So let's apply this information to hydrogen. When a material containing hydrogen is placed in a magnetic field, the hydrogen atoms, which we consider to be protons with spin, begin to precess because of the presence of the force from the static magnetic field. When a radio frequency pulse is applied to these precessing photons, the effect is to cause their angle of precession to change, causing what we call a nutation or a flip from one angle to another. When the frequency in the applied radio frequency pulse matches the precessional frequency of the proton, there is resonance. That is where the term magnetic resonance spectroscopy or magnetic resonance imaging comes from. Currently, the precessional frequency used in MRI systems is that of hydrogen. The precessional frequency of the hydrogen atom is shown in the table above. A hydrogen atom or proton having spin is classically like a bar magnet, even though its magnetic moment is undetectable. On a macroscopic scale, protons are randomly aligned, so there is no bulk magnetization. When the material is placed in a strong static magnetic field B0, it becomes magnetized with a net magnetization vector as protons line up along the field. This is shown in the top left figure. Because protons in this orientation have spin, in the static magnetic field they experience a torque that causes the magnetization vector to precess as it spins on its axis. This is shown in the bottom left figure for a single proton. The precessional frequency is omega naught and is related to the static magnetic field by the Lamour equation. The quantity omega naught is the Lamour frequency. The constant gamma in this equation is the gyromagnetic ratio. The gyromagnetic ratio is an intrinsic property of a material. It is the ratio of a material's magnetic moment to its angular momentum. Different gyromagnetic ratios of a few elements are shown in the table. This figure shows the bulk magnetization vector M0 on a macroscopic scale. The bulk magnetization vector M0 is in equilibrium in the static B0 field. It has two components, a longitudinal component Mz and a transverse component Mxy. The longitudinal magnetization is parallel to B0 and the transverse magnetization is perpendicular to B0. When an electromagnetic wave having the same frequency as the precessional frequency of the protons in the bulk sample, the magnetization vector M0 is nutated or flipped onto the xy plane to produce a maximum transverse magnetization Mxy. The magnetic component of the electromagnetic wave that causes the flip is called the B1 field. This process is called excitation. As the net magnetization M0 returns to its original orientation or equilibrium position, both Mz and Mxy change, and an RF signal is produced called a free induction decay signal. This figure shows the flip angles produced by the B1 field. We shall see later when we learn about pulse sequences that common flip angles are 90 degrees or 180 degrees. So far, we have learned about the rotation of an object in a magnetic field. We used the model of a hydrogen atom or proton with spin and placed it in a magnetic field. We saw that when the proton is in a static magnetic field, it will have a bulk magnetization that is in equilibrium with the field. The bulk magnetization precesses due to the presence of spin and the magnetic force due to the static B0 field. When an electromagnetic pulse or radio frequency pulse B1 is applied to the precessing proton, it nutates or flips onto the XY plane and generates a MR signal called the free induction decay signal as it returns to equilibrium. On the following slides, we shall look at T1 relaxation and T2 relaxation times of the MR signal. In MRI, we are interested in signals produced by different tissues as the transverse magnetization vector MXY returns to its original position following a 90-degree pulse. This decay or loss of phase coherence is what produces the free induction decay signal. Loss of phase coherence follows an exponential decay and has a time constant T2 as shown by the formula. Time between peak transverse signal and 37% of the peak is called the T2 relaxation time. In MRI, the transverse magnetization MXY for different tissues return to their equilibrium position at different T2 times, leading to different free induction decay signals. Differences in T2 times is used to create T2 contrast weighting, which we shall learn about shortly. When a sample is placed in a magnetic field, Because of magnetic field inhomogeneities across the sample, there are variations in the frequency of precession within the sample volume, leading to a different T2 relaxation time called T2 star. Because magnetic field inhomogeneity is a property of the MR system and not of the sample, we try to remove the T2 star component of the free induction decay signal. This may be done by applying a 180-degree rephasing pulse. I will describe that when we learn about spin echo pulse sequences. In the previous slides, we learned about the decay of the transverse magnetization vector MXY. If you recall, there is also a longitudinal component MZ. The return of the longitudinal magnetization vector MZ to its original value is called T1 relaxation. It is governed by the equation shown above. T1 is the time needed for recovery of 63% of the longitudinal magnetization vector MZ after a 90-degree pulse. Different tissues have different T1 values. Differences in T1 values is used to create T1 contrast weighting. Proton density is a fundamental property of tissues and can be exploited to achieve different MR signal strengths. Selections of different T1 and T2 can enhance proton density differences, leading to contrast based on proton density differences. T1 and T2 depend on molecular motion, molecular size, and molecular interactions as the top figure shows. Because most tissues of interest for clinical MR applications are intermediate to small-sized molecules, tissues with a longer T1 usually have a longer T2, and those with a shorter T1 usually have a shorter T2. The table shows a comparison of T1 and T2 values for various tissues. T1 values are longer for higher field strength magnets, while T2 values are unaffected. T1 values are also longer than T2 values for different tissues. T1, T2, and T2 star decay constants, as well as proton density, are fundamental properties of tissues and can be exploited by machine-dependent acquisition techniques in MR. Now let's learn about pulse sequences. All pulse sequences have in common the use of RF pulses to flip the bulk magnetization vector at some angle with respect to the static magnetic field. The main pulse sequence parameters are echo time, repetition time, and inversion time. Repetition time TR is the period between V1 excitation pulses. Echo time TE is the time between the excitation pulse V1 and the appearance of an induced echo. Inversion time TI is the time between an initial inversion or excitation RF pulse and a 90-degree readout pulse. There are three main types of pulse sequences: spin echo, gradient echo, and the inversion-recovery, which is a type of spin echo. We shall learn about each of these on the next few slides. Contrast weighting can be performed based on T1, T2, or proton density. The MR signal strength S following a RF pulse is given by the formula shown at the bottom. By selecting a short TR and a short TE, we can differentiate different tissues according to T1 relaxation times. This is called T1 weighting. T1 weighting uses a TR of between 400 to 600 milliseconds and a TE of between 5 to 15 milliseconds. A T1 weighted image is shown with fat having the most intense signal, followed by white matter, gray matter, and CSF. Contrast based on proton density differences is achieved by reducing the contributions of T1 recovery and T2 decay as shown on the bottom image. In this case, a long TR and a short TE are used. TR values range from 2000 to 4000 milliseconds, and TE values range from 5 to 30 milliseconds. A proton density weighted image is shown with CSF having the highest signal strength, followed by gray matter, fat, and white matter. In T2 weighting, a long TR and long TE are chosen. TRs range from 2000 to 4000 milliseconds, and TEs range from 80 to 120 milliseconds. A T2 weighted image shown here demonstrates high tissue contrast compared with either the T1 weighted or proton density weighted images. The highest signal strength is CSF, followed by gray matter, white matter, and fat. This is shown in the top figure. Let's learn more about the spin echo pulse sequence. A spin echo sequence describes the excitation of the magnetized protons in a sample with an initial 90-degree RF pulse, followed by a 180-degree refocusing RF pulse. Finally, a 90-degree readout pulse is applied. The 180-degree RF pulse inverts the spin system and reduces T2 star effects. T1, T2, and proton density contrast weighting are all done with a spin echo pulse sequence. Typical TR and TE values for spin echo pulse sequences are shown in the table. The signal strength of a spin echo pulse sequence is shown by the formula at the bottom of the slide. A special version of the spin echo pulse sequence is the inversion-recovery pulse sequence. This starts with an inversion pulse, and then the remaining pulse sequences are just like a spin echo, where a 90-degree pulse is applied, followed by a 180-degree refocusing pulse, and then a 90-degree readout pulse. Because the first pulse is a 180-degree inversion, the longitudinal recovery time is doubled when compared to a regular spin echo. Inversion-recovery pulse sequences are used for special imaging, as we shall see next. A special application of the inversion-recovery pulse sequence is short tau inversion recovery. Short tau inversion recovery starts with a 180-degree inversion pulse, causing the longitudinal magnetization MZ to start at negative 180 degrees as shown in the top left figure. Once the recovery reaches the 0-degree line, a 90-degree pulse is applied as shown. The effect of the 90-degree pulse is to create a bounce point as shown on the 0-degree line on the right figure. All tissues go through the bounce point. By selecting an appropriate inversion time Ti, we can suppress signal from different tissues. In the images shown, Ti is chosen to suppress the fat signal, so the signal intensity from fat is shown as black. Another special application is fluid attenuation inversion recovery, or FLAIR. In a FLAIR sequence, the same approach is used with a 180-degree inversion pulse followed by the 90-degree pulse. The inversion time is the time between the 180-degree pulse and the 90-degree pulse. Once tissues cross the zero line, the 90-degree pulse can be chosen at a particular inversion time Ti. In the bottom figure, Ti is set to the null point of CSF, so the signal from CSF is suppressed. The signal intensity from CSF is black as shown in the top image. Fast spin echo or FSE techniques use multiple 180-degree refocusing pulses with corresponding digital data acquisitions per repetition time interval. FSE techniques have the advantage of a spin echo image acquisition, namely immunity from external magnetic field inhomogeneities, but image acquisition is 4 to 16 times faster. FSE is also known as turbo spin echo or RARE, which is rapid acquisition with refocused echoes. A summary of spin echo pulse sequences and their advantages are shown here. MR contrast schemes for clinical imaging use the spin echo or an inversion recovery variant of the spin echo pulse sequence for many examinations. The advantages of the spin echo and inversion recovery spin echo sequences are that they are less sensitive to magnetic field inhomogeneities, magnetic susceptibilities, and generally give higher signal to noise ratio and contrast to noise ratio. The downsides are the relatively long repetition times and correspondingly long acquisition times. The next basic pulse sequence I mentioned is the gradient echo. The gradient echo technique uses a magnetic field gradient applied in one direction to cause a dephasing and then reversed to cause a rephasing. This induces the formation of an echo and replaces the 180-degree inversion pulse used in spin echo pulse sequences. In gradient echo, tissue contrast is dependent on flip angle, repetition time TR, and echo time TE. With moderate flip angles of 30 to 60 degrees, differences in tissue contrast are based on T2 to T1 ratios. When using very short TRs, smaller flip angles require less time and create more transverse magnetization compared to larger flip angles. The image on this slide shows the schematic of the gradient echo pulse sequence. There are special gradient echo pulse sequences that we can look at on this slide. Most gradient echo pulse sequences use short TR times, but we can also use gradient echo with a longer TR time. When gradient echo is used with long TRs greater than 200 milliseconds and flip angles greater than 45 degrees, contrast is like that of a spin echo pulse sequence. The major difference is that image contrast is based on T2 star rather than T2, because external magnetic field inhomogeneities are not cancelled. Recall that we cancel T2 star effects in spin echo sequences with the 180-degree refocusing pulse. In a gradient echo sequence, there is no 180-degree refocusing pulse. In most situations, however, gradient echo imaging is not useful with long TR, except when contrast produced by magnetic susceptibility differences is desired. Gradient echo is often done with short TRs. When gradient echo is done with a short TR, the transverse magnetization does not fully dephase, leading to the production of two signals: the free induction decay signal produced from the RF pulse just applied, and the stimulated echo from residual transverse magnetization. These two signals are used to produce coherent, incoherent, or steady-state free precession gradient echo sequences in order to generate different contrast weighting schemes. We shall look at the various gradient echo sequences from the use of short TR next. Coherent gradient echo uses two signals to produce the image. Contrast in coherent gradient echo depends on the ratios of T2 to T1 weighting or ratios of T2 star to T1. Examples of coherent gradient echo are the GRASS, FISP, and FAST pulse sequences. In certain applications, such as in MR angiography, GRASS pulse sequences are used to produce bright blood signals as shown on the top image. Spoiled transverse magnetization gradient recalled echo, or SPGR, is often used in three-dimensional volume acquisitions because of the extremely short acquisition times. This is because it uses extremely short TRs and TEs. For the image shown, TR is 8 milliseconds and TE is 1.9 milliseconds with a flip angle of 20 degrees. This gradient echo sequence produces contrast based on T1 weighting. This is because T2 star influences are reduced by introducing incoherent phase differences from pulse to pulse. The image shows a spoiled gradient echo image showing the T1 contrast appearance and bright blood signals. In gradient echo sequences with short TR less than 50 milliseconds, the echo time TE is also very short, and so there is very little T2 contrast generated. Also, the echo contains both T2 star and T2 weighting because of poor rephasing. One application is in the steady-state free precession pulse sequence. Steady-state free precession produces signals mostly from the stimulated spin echo portion from residual transverse magnetization. A rewinder gradient is used to position each stimulated echo just before the next pulse. Steady-state free precession sequences are more T2 contrast weighted and are useful for brain and joint imaging and can be used with three-dimensional volumetric acquisitions. The bottom image shows the balanced steady-state free precession sequence. This sequence is useful for reducing patient motion in gadolinium contrast studies. Another pulse sequence is echo-planar imaging. Echo-planar imaging could be done using a spin echo, a gradient echo, or a hybrid of the two called gradient and spin echo. Echo-planar imaging acquisitions have poor signal-to-noise ratio and low resolution because it uses matrices of 64 by 64 or 128 by 64. There are also different artifacts associated with echo-planar imaging. Because of fast acquisition times, echo-planar imaging is emerging as a clinical tool for studying time-dependent physiologic processes and functional imaging. Let's finish up with a few questions. First question: which of these is affected by the static magnetic field strength? Your choices are T1 relaxation, T2 relaxation, proton density weighting. The correct choice is T1 relaxation. Next question: the highest signal-to-noise ratio is produced by which type of tissue weighting? Your choices are T1 weighting, T2 weighting, proton density weighting. The correct choice is proton density weighting. Next question: the highest contrast is produced by which type of tissue weighting? Your choices are T1 weighting, T2 weighting, proton density weighting. The correct choice is T2 weighting. Next question: which of these is not true about spin echo sequences used in clinical imaging? First choice: they are less sensitive to magnetic field inhomogeneities. Second choice: they are more sensitive to magnetic susceptibilities. Third choice: they have high signal-to-noise ratio. Fourth choice, they have high contrast to noise ratio. The correct choice is the second choice. This statement is not true about spin echo pulse sequences. This is the last slide. Thank you for watching this presentation.